welcome to the last day of the workshop. And the first speaker is Shashank, and it's his second talk. Thank you.
Thank you. So I made a little mistake yesterday. So let me correct that first. So yesterday we saw two Rogers-Ramanujan identities. This is the first one. Okay, q to the L square divided by the q poke hammer, and on the right hand side you get a product over congruence classes plus or minus 1 mod 5. Okay. The second one I didn't present this identity, but I did mention that this second one comes with regards to the tail of this torus knot, and at that point I made a mistake. So this is correct, this is q to the L squared plus L, but I got carried away yesterday and I wrote the same product again. It's not the same product, of course, it's different. It's j congruent to plus or minus 2 mod 5. Okay. So and the tail is this q series, that is either of these times q infinity. Okay. And in their paper they proved by doing one way that it is equal to that, by doing other way it is equal to that, right. So two different ways, and then they proved equality. And yesterday I said that this is everything else is correct. So this was a mistake yesterday that I made, so I was just explaining. So just copy this down. If then I motivated that the limit of the two Rogers-Ramanujan identities, if I divide them and take q goes to 1, you get a nice number here. So today what I am going to talk about is just one identity at a time. Each of them has a singularity at q goes to 1, and it's not the limit then that's important, it's how each of these q series approach, or what sort of a singularity does each of these q series have at q goes to 1. So I want to figure out exactly what happens as q goes to 1 for these individually. Okay. That will lead us to asymptotics and dialogarithm. So I would like to explain that, and the reason I want to look at that is the following. I briefly mentioned in passing yesterday that such products are very easily seen to be modular, but it's a very hard, I think it's an open problem to prove the modularity of such a q series presented in such a form without using the identity that that is equal to the product. Okay. Modularity is manifest from the product side. The hard or open problem is to prove it just for things of this expression. Okay. There are many q series of that look like this for which there is no product, so it's hard to guess their modularity. Okay, so what is modular forms? Okay, so of course you know the group SL2Z of determinant 1 matrices so a function from the upper half plane to the complex numbers is called a modular form of weight k if f is holomorphic, okay, f of tau f of a tau plus b divided by c tau plus d is c tau plus d raised to k. K is the weight of f of tau, where tau is in the upper half plane and f is holomorphic as tau goes to I infinity. Okay. This here, the reason is that what you want to do is tau is in upper half plane, you take q is e to the 2 pi I tau, then q is in the unit disk punctured, and as tau goes to I infinity, q approaches 0. Oh, q is holomorphic in H. So this is at upper half plane doesn't include infinity, so I am just also imposing a condition as what happens at a cusp. Okay. Right. And so really what you are saying is that there is a nice it's holomorphic as t goes to I infinity, which means at q equal to 0 there is a nice Fourier expansion. Okay. Now, this is all well and good, but turns out that these are too restrictive conditions for us. So, you need to relax many of these, and I will not give the precise relaxation, but I will just indicate what all people relax in these conditions. So, instead of, so the point is to get some sort of a transformation property with regards to, I here did not mention that ABCD belongs to SL2Z. The point is to get some sort of a transformation property with regards to elements in the modular group, and sometimes you need to relax SL2Z to A. So, you may not impose, you may not stipulate that it transforms under the full modular group, but maybe a finite index subgroup gamma in SL2Z. Okay, sometimes you need to do that. Okay, sometimes this transformation is not very exact. You sometimes need some scalars here. Okay, I will show you an example. So, sometimes the transformation comes with what are called multiplier systems, especially if the weight is half integer. I will show you an example. And sometimes you need to relax this condition of holomorphicity as t goes to I infinity. So, you might require it to have a pole or some other things, but anyway. So, relax holomorphicity in different ways. Okay. I will not spell out what these are, because there is too many relaxations and they come up with too many adjectives, but this is the main idea, is to get some sort of a transformation property. Okay. So, here is an example. Okay. So, sometimes I will write functions with q as the variable, in which case the meaning is that q is e to the 2 pi I tau, but sometimes I will write them with tau as the variable, which means that tau is in the upper half plane. I might switch around. Okay. This is called the Dedekind Eta function, and you are very familiar with this object. This is a modular form of weight half, and I am not relaxing anything else. It is just, I said that sometimes you need to relax it to a finite index subgroup, but here the transformation properties are for all of the SL2Z. So, written in terms of tau, it reads e to the, so here it looks like I am choosing a root of, or rather 24th root of q, but this is the precise meaning. I should write the product over j, because there is a square root of unity that is also there. Okay. And the transformation properties are, well, the most important one I will write down, I will let you figure out. The other one is some square root eta of tau. Okay. So, this is the S transformation. Okay. Yeah.
I'm confused.
Yeah.
In the first line,
yeah.
You use eta of q.
Yeah.
And in the third line, you also use eta of q.
Right. So, sometimes I will write the function with q as the parameter, and sometimes I will write it as t as the parameter. You might want to differentiate them, like put a tilde on top of it, but typically it is semantically clear. When I put tau, I mean tau in the upper half plane. When I put q, it is in the unit disk. Okay. Yeah. I will not distinguish between these two. Okay. So, here you see that it is a weight half modular form. So, you should see something like tau to the half. So, you see tau to the half, but there is also a scalar that you are multiplying by. So, that is the multiplier system that I was talking about. You are multiplying with a fixed chosen square root of minus I. So that's an example of this multiplier system that comes about, where the transformation is not exact. You need some scalars to make it work. Okay.
The modular form over PSL2Z or SL2Z?
They say it over SL2Z.
But the transformation is with respect to PSL2Z.
That's right. Yeah, but they say it over SL2Z, I think.
Yeah, by
Yeah.
pullback at the
Yeah.
yes, but that's a good.
Yeah, maybe to
minus one element act.
that's a good question. Let's see. Well, minus one element doesn't do anything because this is still f of tau, right? It's oh no, right. So turns out that there are okay. So
No, minus one in SL2Z.
that's right. So that will mean that it's A is minus 1 and D is minus 1.
And everything in minus.
Right. So turns out there are no modular forms of odd weight. So this k is always even. So that takes care of it. Okay. So right. Okay. But that's a good question. Yeah. Okay. Now you know that this is inverse of the partition. This is 1 over the partition function that we saw yesterday. Okay, so lesson has another S is that up to modular anomalies or so this small little factor, infinite products have a good chance of being modular. Not all products are modular, but many of them are. And an example is, I will indicate how you prove this later. The product in the first Rogers-Ramanujan identity times q to the negative 160 and the product in the second Rogers-Ramanujan identity times q to the 11 over 60. Both of these are modular forms of weight 0 for an index 60 subgroup of SL2Z. Okay. It's the product, okay, that you get on the nose to be modular. The reason is that these products are related to theta functions, and theta functions are manifestly modular. Okay. I will not say more about this because I want to I will give you a reference. I just wanted to make a point that products are the ones that are immediately modular, and we want to ask the questions, what happens for this guy? Okay. So what can we say anything about modularity of such series when we don't know, for example, that they equal a product? There are many series for which we don't know if they are products or not. Some are conjectured to be products, but it's not proved that they are products and things like that. Yeah. Take the product in the Rogers-Ramanujan one, which is plus or minus 1 mod phi.
Yeah, but the sum there equal, right?
The sum there equals that,
Yeah.
right?
So why like just take product and not the sum?
That is a good question. So as I was saying, it's hard to prove modularity of the sum side just by itself. So I'll give you an example, and I'll tell you who this example is due to later. Take this Q series. Okay, it's written in the form like the sum side of the Rogers-Ramanujan identity. Is this modular? If I tell you that this equals a product like so, if, okay, you can immediately tell me that it is modular, because I can write this in terms of theta functions and eta functions. Okay. The point is, it is a conjecture that this equals that, it is not known. Okay.
I see. So the whole non-conjecture thing is that there is a sum side expression, and he conjectures that it's modular without really knowing the product.
That is right. Yeah. And there are many things that are modular, but they are also not products. But in a very small world where I am looking at things that equal products, even then, can you just independently tell me this is modular? That is just the question. Okay, so what is the idea? The idea is, so this is an open question, by the way. I do not think it's a philosophical question. It is conjectured to be equal to that. Okay. So, the idea is that it is possible to give necessary conditions for a series in this sum side form to be modular, but it is hard to get sufficient conditions. You can get necessary conditions very easily, and the main idea behind these is calculating the asymptotics. So, precisely figuring out what happens as q goes to a root of unity, in particular q going to 1. Okay. And again, these have exponential singularities as q goes to 1. You cannot plug in q equal to 1 in any of these products, right. So, we want to figure out what is the asymptotic expansion. So, what is asymptotic? So, definition, I say that f is asymptotically equal to g as x approaches x naught if f x divided by g x approaches 1 as x approaches x naught. Okay. This is called asymptotically equal, all right, and you can relax this condition. I will say f x is big O of g if approaches some constant, and I will say f x is little o of g as x approaches x naught. Of course, you can write it all there if f x divided by g x approaches 0. Okay. And what we will do is we will analyze. So, take f of q to be so there is this modular anomaly which I will, it's just q to a factor, we will plug in q as e raised to minus epsilon so that this works. Okay. As epsilon goes to 0 plus, q will go to 1 from like so. It is a radial approach.
Could you just say something
Yep.
about the monomials which are there at the beginning of this series? Like they just appear to make it modular, or like what's the
Which monomials?
the that term, and even
Yeah.
in that there's this q to the power minus 1 and all of that. Like if you remove that,
It will not be modular. Yeah, it will
Very
not.
sensitive.
Huh?
Those
Yeah, it's
very
sensitive. Yeah,
to
yeah,
the-
yeah. They come right out of the theta function analysis.
I see. So they are very critical. Like if you just kind of
Yeah.
say q to the power 12 by
Yeah.
16,
Yeah.
you stop the model.
Mhm. Because this S transformation, this tau going to e to the rather tau going to minus 1 over tau, it does something weird to the q, because q is e to the 2 pi I tau. So, this S transform does e to the minus 2 pi. So, it is happening in the exponential. So, it's a little weird. Okay. All right. So, the fact is, I was going to give a short proof, but maybe not. I will indicate where the proof is. It's very
Epsilon tends to derive by through real values.
real values. Yes, it's a radial approach. Okay. The fact is following. Let capital F be a modular form of weight k for some finite index subgroup gamma of SL2Z, then there exists an alpha, a rational multiple of pi squared, such that okay. So, I will write it as f of q so that you do not get confused with tau and q, e to the f of, so this is our q, remember, yeah, this is asymptotically some constant epsilon to the minus k, this k is the weight, plus little o of for all okay. So, modular forms have a very specific kind of asymptotic expansion. This is the root of the exponential singularity that I was going to talk about. So, for us this alpha will turn out to be a negative number. So, I will put it on the other side, it will become a positive number, but anyway that is later, forget about that, but this is exactly what is happening. Okay. So, now if you could figure out asymptotics from the sum sides and you could ascertain that they look like this, you have got a necessary condition for, you have satisfied a necessary condition for being modular. That is the idea. Okay. Rational multiple of pi squared. Okay. Let us take an example.
In that small order, like which point are you considering?
As epsilon goes, yeah, good point, as epsilon goes to 0. Okay. Let's, it's great to prove things by examples. So, let me give you an example. Okay. So, we saw that for tau in upper half plane, this is square root of minus I tau. Okay. Now, put tau as 2 pi I over epsilon. So, really I should move to the q world. It's 2 pi I tau, which is okay. So, when I write this in terms of q's, what do I get? Eta of e to the minus 2 pi I over tau. So, this is written in terms of tau. Now, let us write it in terms of exponentials. Okay. Again, this is confusing, I completely understand. I have written this in terms of an argument that is in upper half plane, but here the meaning is that the argument is in the disk. So, yeah.
This expression, what does it mean to say for all n greater than equal to 0?
So, the error is something like, so here it ends up that the error is something like e to the minus 1 over epsilon. So, if you divide by any power of epsilon to the 2, 3, 4, whatever, it decays faster than any epsilon to the n. So, this error term is such that it decays faster than any epsilon to the n. So, it is something like this. Okay.
So the point is that as it
Yeah.
the boundary,
Yeah.
you are able to detect the weight of the form.
Yes, precisely. Yes, weight of the form, and also this condition is going to lead to a severe constraint on the dialog. It's not a severe constraint, I don't know, but this will lead to a constraint on the dialogarithm. Okay. Yeah, that's good question. Okay. So here I am thinking of eta as a function on the unit disk, and here I am thinking of eta as a function on upper half plane. So it's a little confusing, but this is the one I need. So let's plug in. So I always make mistakes at, no, that's correct. Okay, so let's plug it in. Tau is 2 pi I over epsilon. So eta of e to the minus epsilon, okay, let's just plug it in, is minus I times tau is 2 pi I over epsilon, okay, and eta of e to the 2 pi I tau, how does that look like? Well, remember this is eta of q is q to the 1 over 24 times all that. So let's plug it in. Q is e to the minus 4 pi square over epsilon over 24, and then there is an infinite product. Let's write down just how it expands. The first term ends up being something like this. Just expand and write down the first few terms in that infinite product. Okay. So this is that here, and I'm just, so this is that 1 over 24 term. Okay. And what do we get? I think I'm being a little confusing, so you might have to go back and spend 2 minutes on what I'm doing, but hopefully this. Okay. This is now a constant times epsilon raised to a negative half, right? There is this exponential, let's put it on the left hand side. So e to the pi square over 6 epsilon, and then I'm left with all of these guys, and they are precisely of the form order of epsilon to the n for any n bigger than 0. Okay. So I have put this exponential on the left hand side, so it's just this times that minus this times an exponential, but this exponential decays very fast as epsilon goes to, oh, this is epsilon, why did I write an alpha? Okay. And I showed you that, or told you that eta has weight half, so you should get really epsilon to the minus half by that theorem, which is what you see here. Okay. The point is, you look at the transformation property of eta and you get it in one step.
Is there a unique case for which negative
Yeah.
If you get such a thing, can you always say it is a free case?
Yeah. Okay. So now let's move on to the asymptotics for Rogers-Ramanujan. For so what I will do is I get scared doing analysis, so I put it on computer. Okay.
So how did you do this computation? I mean, is it like
yeah.
easy, straightforward, or like it's
So the key thing is knowing the modular transformation property. Once you have that, this is just one step. I am just plugging in tau as 2 pi I over epsilon. That's just what I did. This is one step. The hard part is knowing this modular transformation property, for which look in the book of apostille.
No, this particular model.
So I did it particularly for eta, but the proof of that fact proceeds by just writing down an abstract transformation property and just analyzing what happens.
What do you need on that modular form for that?
Nothing. You just need to know that. You just need to know some sort of a. I mean, you just need to know this here, an equation of this sort. What happens when you put tau to -1 over tau? You just need some placeholder for that. So the proof of this fact you can find in. It's very short. It's a short paper on Nam's conjecture. Okay. It's very short. It's just this done abstractly. That's it. Okay. So I want to know what happens when I plug in values of q approaching 1. What happens to this series? So let's plug in some values. So on this axis, I'll plug in L is our summand, and I'll plug in the value of the summand. So this is a sum over many L's. So let's take q equal to 0.97. Okay, you plot L equal to 1, what is this summand equal to? L equal to 2, what is this summand equal to? You get a nice graph. The peak is at 16, and the peak is roughly of the size 10 to the 8. Did I make a mistake?
No, I'm wondering why did you pick this sum when in that formula
Yeah.
the -1 times 6?
Good question. So I just wanted to show you by example that modular forms have this type of transformation property. So I just showed it with an example of the eta. Okay. You could do a similar thing with the products in the Rogers-Ramanujan identity, which I am not showing here. But now really what I want to do is analyze sums in the Rogers-Ramanujan identity. I just wanted to show an example, so I picked eta. That's all I did. It has nothing to do with Rogers-Ramanujan.
This is now more general.
This is now well, I'm analyzing the specific case of Rogers-Ramanujan, so it's different, not general.
So the
Yeah.
even for the partition function,
Yeah,
did Ramanujan know this is a modular?
probably. I don't know. Probably he knew. He must have. I don't know really. Yeah, but he was good at knowing asymptotics, so maybe he knew. Yeah. Okay. All right. So let's plug in 0.97 for q. You get the peak at 16. Let's approach. You get a much taller peak. The peak happens at the 48th summand, and this is of the order 10 to the 27. You can do this on Mathematica very easily. Okay. All right, and you can see that as q is approaching 1, it's growing very fast. That is the nature of the exponential singularity. And I'm going to add all these terms to get what this is. But let's focus our attention on the most dominant term, which is this peak, right? So where do you get this peak?
You are just plotting what happens to the summands when you are taking q close to 1.
Right. Yeah. Okay. So now for a fixed q, take it to be very close to 1. You can see experimentally that this is a unimodal sequence of summands, meaning it has a unique maxima. Where does the peak occur? The peak occurs, you can see this experimentally, when two nearby summands give you very similar values. They are not equal, but 48 and 49 or 48 and 47, they will give you very similar values, right? The whole slope has to be 0 there. So let's plot that condition, or let's analyze that condition. So you get a peak roughly at the nth summand if the nth summand is approximately equal to the next one. So solve this. Okay, this is 1 minus q squared dot 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 up to 1 minus q to the n plus 1. this stops at 1 minus q to the n. So, this tells you that roughly speaking this is approximately equal to 1 minus q to the n. Okay. So, where the summand occurs, the biggest one is dependent on the value of q, and so as q goes to 1 happens at that n where q is going to 1. So, it is really q to the 2n is approximately equal to 1 minus q to the n. So, if I plug q to the n as a z, then I get z square is equal to 1 minus z, okay, and I want z to be between 0 to 1 because q is in between 0 to 1, and here it is which is the inverse of the golden ratio. Okay. So, the point of showing you this was that the most dominant term that is controlling this expansion, the asymptotic expansion, happens at a very specific summand. It is related to q. Okay. So, if you take q to be very large, the summand at which it happens will satisfy this inequality, this equality, okay, that q to the n will be roughly the inverse of the golden ratio. Okay. Now, let us look at the asymptotics of that summand. So, let us focus on that summand and see what it gives us. So, here is where the dilogarithm comes in. So, now we will focus on that summand, just that, and it looks like that. Okay. So, let us have this q series which is dot 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 up to, right, it just goes on up to ad infinitum. Let us look at, right, a truncation of this is what you see below, but n is large, right. So, let us first understand what happens to this here. Okay. So, I would like to know what are the values that this guy takes. So, this is I have to do this because I am going to cheat a little bit. Okay. Let us take the logarithm of this. What do you get? It is summation of log of 1 minus t q to the j greater than or equal to 0, all right. Okay, let us expand. So, my sign says m greater than or equal to 1 t to the m q to the j m divided by m. Okay. Switch the order of summation, you can do all that. I get no joy in being rigorous. You can do that if you want to figure out the epsilons and deltas there. So, let us switch the order of summation. Just let me know if I am not doing anything correctly. You can find a precise proof in the paper of Lasenko and Zweigers, right. I think I have switched it correctly. Maybe, yeah. Now, this is a geometric sum 1 over 1 minus q to the m. Okay. Remember, as q approaches 1, 1 minus q to the m is roughly equal to m by L'Hopital, right. So, I will write this as times, okay, All right. What is this? So the sum is over m bigger than 1. So let's pull out the minus 1 over q. Okay. What is this? This is dilogarithm. Okay. So this is okay. This function has a name. Any guess what it is? Starts with a Q. Quantum dilogarithm. Okay. All right. And now, again, we are cheating anyway, changing summation. So let's cheat some more. Is this? So this is roughly like dot dot dot. Plug it in here. 1 minus this. So this is that. Like this plus roughly equal to. Yeah, I'm ignoring the higher order terms. Epsilon is very close to 0. Okay. All good. So what do we want? We want this divided by this is this is small n. This is precisely what you see in this summand below. Okay. All right. So I'll just put t equal to q to the n plus 1. N was this summand where you got the biggest one. I'll divide by this. You get this, which you saw in that summand. So what is this? This is, now we know what this is. This is minus okay. So log of this is, I'll just take t equal to q to the n plus 1 here. I'll take t equal to q and subtract. Li2 of q. Okay. Now as q goes to 1, we saw before, well, q goes to 1, so q to the n plus 1, and we are keeping q to the n equal to that z because q is very close to 1. So n is such that this peak happens at q to the n equal to z. So this is Li2 of z plus 1 over epsilon. Q is going to 1, so this is Li2 of 1. Okay. So now you see that Q pocamers are asymptotic to dilogarithms. Okay. What is Li2 of 1? Pi squared over 6, it is zeta 2. Just plug in, where was it? I forget. Here. Plug in t equal to 1, you get pi squared over 6. So this is okay. So we found the logarithm of this term, which means that we don't want logarithm, we want the term itself. Is roughly e to the that okay, all good. There is one thing which I have not written here. There is it's not this term that is dominant, it's this term that is the big boss, right? Turns out if you just do this analysis, I won't do it right now. It is very easy. Just look at the fact that q to the n is equal to z, q is e to the minus epsilon. You do that part, here you will get that this is in fact the Rogers dialogarithm. Okay. What is Rogers dialogarithm? It is the actual dialogarithm plus half ln x and ln 1 minus x, and you define L of 1 equal to pi squared over 6. You do not have to define it actually, that is the limit as x approaches 1, it is easy to prove, and L of 0 is 0. Okay. Again, you cannot plug in 0 here or you cannot plug in 1 here, but the limit as x approaches these two is this. So, it is a removable. All right. So, this is, now you know what this is. This is e to the 1 over epsilon times a number, right. Okay. I have showed you only the most dominant term. The analysis is not complete. You have to add infinitely more terms to this because the Rogers-Ramanujan sum has many more terms than this dominant summand. So, either for the full asymptotic analysis, look in the paper of Vlasenko and Zweigers. This is quite general, but there is another paper from, so this is 2011, there is another paper by McIntosh from 95 where all the details that I have suppressed are given, and you will no, no, he's an actual person. Yeah, no, it's he's an actual person. Yeah, okay, and you will see that you actually get this Rogers-Ramanujan sum, the first one as some constant times e to the epsilon term is this divided by epsilon, and then there is a little more, but I will skip that. Okay. All right. So, now you see that this imposes a strong condition, because this means that this number for modularity must be a rational multiple of pi squared. That is a necessary condition for it to be modular. Okay. In general, if you give me a random Q series, then there are more terms in the expansion, and again that expansion has to fit the fact that I wrote down about asymptotic expansion. So, you get more conditions on, this is just one of the conditions, you get more conditions, and they have to be satisfied. So, that is, oh, did I not put z? Z was the root of that, the inverse of Golden ratio, because q to the n is z, right. Okay. All right. Okay. So, I am running quite close to the time. So, I will just tell you briefly in words now two things: Nam's conjecture. Okay. Right. So, this is Rogers dialogarithm. It is known to satisfy some functional equations. Okay. Again, I do not do research in this, so I am just going to look in some paper and write them down on the board. So, instead I will just say that look in this paper of Zagier where he gives all these functional equations, and there is this survey of dialogarithm by Zagier.
This is a remarkable dialogarithm, or this is a different one?
The dialogarithm function.
I see. This is available online.
It's quite, yeah. Okay. And the and people believe that all such identities are consequences of the known functional equations of the dialogarithm function. I think that is what people believe, right? Is it proved? I don't know, but this is what they believe. the functional equations, yeah.
Could you just repeat what
Yeah.
you believe is
So in general, if you give me a random Q series, then you will get a constraint like this, that this dial logarithm is a rational multiple of pi square.
if it's modular form?
If it is to be modular form, okay. People believe that all such constraints are just, all such relations of the dial logarithm values are consequences of the known couple of functional equations for the dial logarithm, okay. And exact values of the dial logarithm, Rogers dial logarithm, are known for only a few points. These are the ones that I wrote down. This is pi square over 12, and this by Rogers-Ramanujan analysis, the value at inverse of the golden ratio is known. But there are many relations like this known, and people believe that they are all consequences of the functional equation. So Nam's conjecture is basically saying that this constraint is a consequence of the functional equations. So he formulates it in terms of the block group of some field, which again of a specific field that is related to the Q series. Okay. And the block group precisely captures these functional equations of the dial logarithm. So you can read about that in the last section of this paper. Okay, so that's what Nam's conjecture is. Okay. Now I thought I'll also mention one sentence. Again, I don't really know what these mock modular forms are. So in the last letter to Hardy by Ramanujan, of course, he gave a list of functions. Okay. He didn't give a definition of what mock theta functions are. I think I was talking to someone and I thought he had given, but no. Someone at lunch, but anyway, I must have made a mistake. He didn't give a definition. He gave examples of what he called mock theta functions, and he gave properties. So what are these properties that his functions he claimed to satisfy is that these are not modular by themselves, but on the radial approach to roots of unity, he claimed that at infinitely many roots of unity you get such exponential singularities, and at any root of unity you can cut out that singularity by choosing a specific theta function. Okay. So meaning you can always subtract a theta function to get an O1 term as you approach the root of unity, but by themselves they are not modular. So these are what mock modular forms are. There is a survey by Gordon and McIntosh on this. It's in 2012. So at the end of the thing I'll give the references to someone, Abhijit, okay, on what these are. And third, now there are very fancy things called quantum modular forms. I absolutely have no idea what they are, but they are related to this strange function. Okay. All right. The reason this is strange is because this object doesn't even make sense as a power series. Each summand contributes 1, so it's 1 plus 1 plus 1, so there is an infinity coming there. It does make sense at roots of unity, and those are the only places where it, I think, converges or something. Those are the only Q's that you are allowed to plug into this. Okay, but somehow this is still interesting and important from knot theory perspective. So this is that. There is again a paper by Zagier. Oh, I see. And Zagier actually gives, so again asymptotics don't make sense for this because it doesn't converge, but Zagier puts in Q equal to e to the minus epsilon, expand this as a power series, plug it in here, then it makes sense as a power series, and he figures out what the coefficients are. Okay. And the last thing I'll say is this conjecture is by myself and Matthew Russell from 2014. We didn't conjecture it in this form, we conjectured it in terms of the difference equations being equal to products. This formulation of the conjecture is by Kirshengos this year, still not proved. There are 4 other conjectures of this kind, very related, and the products are related to this affine Lie algebra called D43 of all things. Okay. If you really get interested, there is another paper by myself and Matthew just this year where we have 13 or 14 new conjectures of this kind, 7 of which have been recently proved by Brinkman, Jennings, Schaefer and Malberg. But there are many conjectures of this kind. And that's it.
So are there questions? So if there are no questions, let's thank the speaker again. Take your
Thank you.